Emission of the hydrogen atom. Alright, so going back to the drawing right here involving the energy levels through which the electron can orbit the nucleus, we know that if we absorb energy, the electron will jump to higher levels. But unless you have a continuous source of energy, the electrons will actually decay back to the ground level, the one where n equals 1. And when the electrons decay back to the ground state, they will emit energy associated with the transitions. And so we could look at each one of the transitions over here. But notice that now n initial will be higher in value than n final. Okay, and we're going to concentrate on the hydrogen atom, so Z equals 1. Okay, so M final, we're going to make 1 automatically for each one of these calculations at the moment. And we're going to see what happens when N initial is 2, 3, 4, 5, or 6. So starting with the value of 2, we're going to find out that 1 minus 1 over 2 squared is going to be 3 over 4. We're going to ultimately find out that all the values we had before are going to pop up again. We're going to have 8 over 9, 15 over 16, 24 over 25, 35 over 36. But this time around, we're going to have the negative outside persisting. It will not cancel out because we have basically swapped the order of n initial and n final. During emission of energy, you actually keep the negative sign of the energy because you're losing energy. That's what emission ultimately represents, the loss of energy. So multiplying this by the Balmer constant gives us some values. But I want to emphasize one more time that the decay of the electron from a higher energy level to a lower one leads to loss of energy in the form of light. And once you introduce the value of the Balmer constant, you actually have energy values associated with each one of these processes. And all of them are negative. So during emission of light, all of the energy changes have to be negative. This cannot be overemphasized. It's very important that you keep track of those two words. Absorption, energy is positive. Emission, energy is negative. Now, what I want you to notice is that looking at the values, going back here, look at the values, all of them are times 10 to the negative 18 joules for the transitions back to energy level 1. You start at 1.6, go up to 2.1, and what you find out is that that roughly falls in the vicinity of X-rays and UV light. So that's kind of the light you will be emitting upon decaying all the way back to the first energy level. We call this series the Lyman Series. So whenever you hear anyone talk about the Lyman series, they're basically talking about electronic transitions from higher energy levels all the way down to the first energy level. But that doesn't need to happen. You could actually decay from a high energy level all the way down to a partial lower one, like the second one. You could actually decay just to the second one before ending up on the first one. And if that happens, n final is going to be 2, so you're going to have 1 over 2 square for your n over 1 over n final square. And your n initial could be any value above it, 3, 4, 5, 6. We're still talking about emission. So in the case where n initial is 3, we're going to have 1 over 4 minus 1 over 9. Carry that calculation in your calculator, multiply by negative 2.18 times 10 to the negative 18 joules, and you'll find out the value is negative 3.03 times 10 to the negative 19. Do the calculation for the decay from the fourth energy level to the fourth energy level. So n initial is 4, n final is 2. You'll find out that the value is negative 409 times 10 to the negative 19 joules. Decaying from the fifth energy level to the second, we know that n initial is 5, n final is 2. So you'll find out upon doing the calculation that the value is negative 4.58 times 10 to the negative 19 joules. And if we start at the sixth energy level, decay down to the second, we're going to find out a value of negative 4.84 times 10 to the negative 19 joules. And all of them, notice, have an exponent of 10 to the negative 19, starting at about 3, ending at about 4.8. And if you look at the spectrum, starting at about 3 and ending at about 4.8, basically falls within the visible spectrum. And this is times 10 to the negative 19. So decaying electrons for hydrogen from higher energy levels down to the second energy level produce light that is visible to us. And the beauty of this is that when you do excitation experiments, you can actually excite electrons to higher energy levels, but when they come back down, they will emit light. And some of this light will be colored light, visible light. And so for hydrogen, we actually see and expect to have lights that match up these particular energies. And by the way, decaying to the second energy level is known as the Balmer series. So for the hydrogen atom and the hydrogen atom only, the Balmer series is understood to be the one leading to visible light, but this only applies to the hydrogen atom. Now, the amazing thing about this is that the model is rather simplistic, and yet when you look at the emitted light of hydrogen, you have a direct match, like it's right on point. And this was basically a mark of victory for the quantum mechanical model, because we went from not being able to explain why is it that putting so much energy into the atom, continuous amount of energy, only produces these amounts of energy and nothing else. It's because of quantum mechanics. And with this simple quantum mechanical model of the Rutherford model of the atom, we have actually predicted each one of the emissions of light of the hydrogen atom. So this is definitely a big victory for quantum mechanics. I'm going to kind of continue this process a little bit further to see what kind of light we get. This time I'm going to decay down to the third energy level. So n final will be 3. N initial is going to be higher, so 4, 5, or 6. In the case where we have n initial be 4, we end up with negative 1.06 times 10 to the negative 19 joules. If n initial is 5 and we decay to the third energy level, the energy is negative 1.55 times 10 to the negative 19 joules. And if we start at n equals 6 and go down to n equals 3, we will end up with negative 1.82 times 10 to the negative 19 joules. They're all 10 to the negative 19, but we start at about 1 and we go up to 1.8. That actually falls, if you look at the energy per photon, that falls below the cutoff for the visible light. So we're actually dealing with infrared light. So all of this is infrared light as the electron decays to the third energy level. And decaying to the third energy level is also known as the Paschen series. Okay, so far we have the Lyman series decaying to n equal 1, the Balmer series decaying to n equal 2, and now the Paschen series decaying to energy level 3. And yes, believe it or not, there's an additional series known as the bracket series, but I'm going to save that for the next video. So for now, I'm going to stop this right here and we'll continue on the next video.